I've started the recording now.
Right, give me one moment. Hello, welcome again to ALP Algebra class number 3, which is about polynomials. So we know that polynomials have degrees, coefficients, and roots, and their leading coefficient. So for this particular polynomial, we actually have 6 as our leading coefficient. Sorry, which 6 is our leading coefficient here because it has it's x cubed, which is the largest degree, and then this means that 6 will be our leading coefficient. Monic polynomials are polynomials such as this one, where the leading coefficient is 1. So in this case, there's nothing in front of it because we don't write ones, but this would be a monic polynomial. And polynomials can be added, subtracted, multiplied, and divided just like any other regular numbers. Anyway. All right, so our first example is adding x squared plus 4x plus 4 plus 2x squared plus 5x plus 9. So we can combine like terms here. So that's what we'll do. So these are like terms. 4x and 5x are like terms, and 4 and 9 are like terms. Like terms are terms where the x degree of the x is the same. So if we add all of these, we get 3x squared. And this would be our answer. Because we've added all like coefficients. So yeah, right here it's how we would solve it by combining like terms. So our next topic is subtraction. And basically, we have 2 polynomials here. We have p of x. We have p of x. We also have q of x. And we have to find what q of x minus p of x is. So q of x minus p of x would equal 2x squared plus 1 minus this plus x squared plus 4x 1. Oh yeah, I'm sorry if you can't see that. But move over a little bit. And then we can subtract like terms. So we would get x to the 5th, or negative x to the 5th, minus 2x to the 4th, and then plus x squared minus 4x, and then plus 0. So this would be our answer after combining like terms. I hope everyone can see that. So this is, yeah, same thing as addition. We combine like terms, but in this case, we would subtract them. Now we have multiplication of polynomials. Basically, we have f of x equals x squared plus 2x plus 4. F of x, and s of x. And then we have to find what f of x times s of x would be. So f of x times s of x equal 4 plus 2x 4 And then there's not much space here, so I'll do it on the next one. But basically, this is what we want to expand, and we expand by using like terms. So if I can make this undo. Give me a moment. Let me erase this. Move it up here. Okay. So now that we have what we want, this equals, we want to multiply each time. So it would be x4 plus 5x cubed plus 9x squared. And then we would do the same thing with 2x plus 2x cubed plus 10x squared plus 18x. And then we do the same with 4. 4x squared plus 20x plus 36. And then we would combine like terms. So x fourth, there's only this. And then the values with x cubed would be 5x cubed and 2x cubed. So it would be 7x cubed. And then 9x squared, 10x squared, and 4x squared would be the same. So that would be 23. Values with x would be 20 and 18. That's 38. And then our constant term would be 36. And then our answer, switch to block, would be this. Yeah. Hopefully, everyone can understand this. Okay. All right. Now we have a polynomial multiplication, which is a theorem. So in general, if we have two polynomials, p of x and q of x, such that q of n times p of n x to the power of n plus n plus dot dot dot, and then we have p2 q0 plus p1 q1 plus p0 q2 x squared plus p1 times q0 plus p0 times q1 x plus p0 q0. Basically this is just having these two polynomials multiplied and we're adding like terms. So another theorem that is usually very helpful is for every polynomials p of x, q of x, and r of x, can be uniquely chosen such that f of x can be expressed as f of x equals p of x times q of x plus r of x. It is required that degree of r is less than degree of p. And this will be explained later. We can divide any two polynomials to get another polynomial as a quotient and plus possibly some remainder. That is also a polynomial. So proof of this is long division. So when we divide p of x by q of x, we first take out the largest factor of q of x that goes into p of x. So the one with the leading term equal to the leading term of p of x, and then repeatedly do this until we cannot take out any more factors of q of x. And then thus we would be left with a remainder such that the degree is less than q of x. So an example of this is shown right here. So we have the x to the fifth plus 3x to the fourth plus 2x cubed plus x squared plus x plus 1. And this is divided by x squared plus x plus 1. So now we go down the list. So we start here. We multiply by x cubed. And if we multiply this by x cubed, we get this and we subtract it. So then we're left with this and then we add the next term comes down. And then we have to get rid of these leading coefficients. So could be 2x squared, because 2x squared times x squared is 2x fourth, which would cancel out this term. And then this x gets, and we keep repeating this until we get a remainder that is not divisible by x squared plus x plus 1. And notice that the degree of 2x plus 1 is less than the degree of x squared plus x plus 1, which is what we stated earlier. All right, the remainder theorem. The remainder when f of x, which is a polynomial, is divided by x minus k, is f of k. So the proof is f of x is a polynomial, and then we divide it by x minus k, and this is our quotient, and this would be the remainder. So if we plug in f of k, this equals k minus k, q of x plus r of k, I guess. Okay. However, since this is 0, this can be canceled out, and we're left with f of k equals r of k. So thus, we've proven it. I'll just stop for a quick moment if people have questions. Also, if you have any questions, remember to put them in the chat. And to people that to either the co-host or to myself, preferably the co-host, because I usually can't see the chat till much later. Coming out of the remainder theorem is the factor theorem. So if r is a root of f of x, specifically f of r equals 0, then x minus r is a factor of f of x. No. X again, the proof is if we take x equals r. So basically, note that f of x equals sum divisor x times quotient x plus r of x. So if f of r equals 0, that means d of x times the q of x plus the r of x will also equal 0. Or in this case, all of these are r actually. So in order for this to be 0, r of x, r of r, I guess the remainder would also have to be 0. And the x minus r is basically would be d of x. Basically, when we plug in r, this would become 0, and then the rest would just cancel out as 0. All right, so now we have a more difficult example. This is from BMC. So we have to find the remainder when x to the power of 81 plus x to the power of 49 plus x to the power of 25 plus x to the 9th plus x is divided by x cubed plus minus x. All right, so 81, 49, 25, 9, 1 is x cubed. So yeah, we know that f of x equals this, and p of x is this, because p of x is what we're dividing by. And if we factor out x cubed equals x 1, so our roots are -1, 0, 1. So this is how we get our roots, by factoring out x cubed minus x. So we know that -1, 0, and 1 are the roots. So now we will proceed to figuring out there. So q -1 equal r of -1. Q of 0 equals r of 0. And q of 1 equals r of 1. Now this is true all because of the remainder theorem that we proved earlier. So this is why this is true. Yeah. Mhm. I'm trying to select all of it. I'm gonna erase all this now that we understand it, just so I have more space to work on the actual problem. So now we can go ahead and solve for what q of -1 is. Q of -1 equals, as we know, the original polynomial was x2 to y1, 29 plus x. So x of -1 would be -5. Q of 0 would be just 0. And q of 1 would equal 5. Now, since we remember that the degree of r of x will be less than what the degree of p of x was, we know that q of x will be at most at degree 2. So we can write this as ax squared plus bx plus c. So now, if we plug -1 in as x, we get 3 equations. We get a minus b plus c equals -5. Now I'm gonna give a little bit. We also get c equals 0. And we got a plus b equals 5. Now if we solve this, we already know that c equals 0. And that means a minus b equals -5 and a plus b equals 5. So then simply a also equals 0 and b equals 5. So thus, if we plug b back in, a, b, and c back into this quadratic, we'll get that the remainder is 5x. And that is our answer. I'm going to leave this on here for a little bit so people can follow. Please come in and ask if you have any questions. All right. I guess I'll move on. So now we have another question. We have the 2017 AMC 12A problem number 23. And basically, in this question, we have certain real numbers, a, b, and c. The polynomial g of x equals x cubed plus ax squared plus x plus 10 has 3 distinct roots, and each root of g of x is also a root of the polynomial f of x equals x to the power 4 plus x to the power 3 plus bx squared plus 100x plus c. So basically, the remainder of x4 plus x cubed plus bx squared plus 100x plus c, when divided by x cubed plus x squared plus x plus 10, must be 0. Now, we know this because since a, b, and c these three are each root of g is also a root of this. Thus, if we can write this as like x minus a, x minus b, and x minus c, we know that this can be written as like x minus a, x minus b, x minus c, and x minus d, which means that g of x will divide f of x. unclear. So we can write this as g of x, which is just this, times x plus q, for some constant q. Now, if we solve this by expanding, we'll get that q is 90 and a equals negative 89. And then after we plug in 1, we can plug in 1 into here, and then we will get our answer. Okay, so now roots. Roots of a polynomial are values of x that make the polynomial equal to 0. Now, if we can graphically define this. I'm having technical difficulties. Sorry. You are getting a quick overview of stuff that we will learn. We're here. So if we can graphically explain this, we have and we have f of x equals like this, some wiggles, wiggles, wiggles. Roots are where it hits the x-axis. Or I'll do them another color so you can see them there. These are all lines. These are all lines. This is x-axis. This is the y-axis. And basically, each of these points will make the polynomial equal to 0. So these are what roots are. Now, let's continue. So we have a fundamental theorem of algebra. Basically, a polynomial with complex coefficients will have at least one distinct complex root. Basically, every polynomial has at least one root, is what it's saying. So now we're asked to find the roots of f of x equals x cubed minus 6x squared plus 11x minus 6. So one thing we can use here, something that we've already known, if f of a, let's just say a is our root, equals 0, then x minus a divides f of x. Thus, let us just try to plug in 1. So f of 1 equals 1 cubed minus 6 squared plus 11 times 1 minus 6. And then we get what? 1 minus 6 plus 11 minus 6, which equals 0. So great. We know that x minus 1 is the root. So now, if we divide x cubed minus 6x squared plus 11x minus 6 divided by x minus 1, we'll get x squared negative 5x squared plus 11x, so we'll get negative 5x. No. 5x, 16x minus 6. Okay. Negative 5x squared. Oh, yeah, so it would be plus 5. So then, I was kind of capping there. So then we get 6x minus 6. So then we would just add 6. Right. So this is our quotient, and our remainder is 0. So Now we got and this we can factor this quadratic pretty easily. So our roots are, and we're done. That's a pretty fairly simple way of solving. I'll leave this on for a bit so you guys can see it. Let's keep moving. So yeah, we realize that x minus 1 is root, and then we divide it out and factor, and then we get our resulting quadratic. Now we have the rational root theorem. So if f of x has a rational root of p over q, such that p and q are relatively prime, and p is a divisor of a0, which is the constant. Basically, a0, which is this, the last term, and q is divisor of a of n, which is the first term. Now, RT is just rational root theorem, like RRT. So it's great for guessing roots. So if we have a polynomial, then sometimes we'll do this and we can find roots. So the proof is very long. So basically, it's suffice to show that any root p over q, which divides a polynomial, f of x equals a of n x to the power of n plus x n minus 1, x to the power of n minus 1, so on, plus a0, where the an's are integers. So if we plug in x equals p over q, then since one side will equal 0, and then the other side will be an p over q to the power of n plus dot 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 0. And then we can multiply this by a certain q to the power of n. So then now we have this. And this also means since all of these, it's 0 mod q, and this is 0 mod p. Because it must divide q and p for everything. And since p and q are relatively prime, this means that a of n equals 0 mod q and a of 0 equals 0 mod p. So p divides a of 0 and q divides a of n. So now we're asked to find the rational roots of 3x cubed minus 5x squared plus 5x minus 2. So basically, you would probably like start out by trying to find roots of these. Like, remember we find p over q, where p divides -2 and q divides 3. So we would use a rational root theorem to list out all possible roots, and then we can test them. So remember back here where p of q, p divides a of 0, and then q divides a of n. So basically, we divide -2, and then things that divide -2 are -2, -1, 1, and 2. Divides 3 are 3, 1, -1, 3. So there will be 16 ways. And I honestly don't want to try all of these. Basically, would be plus or minus 2 over 3. That's where then these one. Plus or minus 1 over 3. And then we do the same plus or minus 2, plus or minus 1. I think this should be it. Might be only 8. Yeah, might only be 8. All right. So we have to find the rational roots of these. So I guess we're gonna start trying some. So if we plug in 2 over 3, we get 3 over 7 over 9. And then we get 8 over 9 minus 20 over 9 plus 10 over 3 minus 2. This would be negative 12, so negative 4 over 3. And this would be 6 over 3, 2 minus 2. So we found that 2 over 3 is actually a root. So now we can factor this out. So the 3x squared minus 2x squared negative 3x squared plus 5x. Then subtract 3x squared, or subtract 3x. Then we have 3x minus 2, and then we can add 3. So we got 3x squared minus 3x plus 3. And then we're going to erase all of these. We have minus 2 over 3. We can factor out 3. Now we just have to, we can use quadratic formula to find the roots of this. Thus, our roots is 2 over 3. And our roots is also 1 plus or minus square root of 1 minus 4c, so minus 4, 1, 1, all over 2, which is just 1 plus or minus square root 3i over 2. I wrote I because this would be negative 3, and so we can take out the negative 1 as I. This is alright. These are our answers. These two, and this one. We're done. Oh yeah, thank you. So Rohan found that this isn't actually rational. So these are actually what do you call it, complex. So these are gone. So our only roots are actually 2 over 3. So very good, Rohan. Okay, and now we are done. All right, so now we have Vieta formulas. Vieta formulas are a set of equations that relate the roots of polynomial to the coefficients of its terms. So Vieta formulas for quadratics. This is actually important that you know these. If you have a quadratic with roots r and s, then r plus s equals negative b over a, and rs equals c over a. So basically, the sum is negative b over a, and the product is c over a. All right, so if we have r and s are the roots, and so p of x is x squared plus b equals c, we can rewrite this as a x minus r, x minus s. That's because r and s are both roots, so x minus r must be a divisor, and x minus s must also be a factor. And basically, if we expand this, we'll get a squared minus r plus s x plus rs equals ax squared plus bx plus c. So x squared minus a plus s. So the sum is just this term divided by negative a, so it would be b over negative a, which equals negative b over a. And the product is just c divided by a. So thus we have proven and we are done. So now we have a pretty easy AMC 10 problem here. So let D and E denote the solutions of 2x cubed minus 5x. What is the value of d minus 1 times d minus 1? So we can first, let's try and not find the actual values of D and E and try to solve smartly. So d minus 1. If we expand this, it's dE minus d minus e plus 1. So then we realize, oh wow, d is product, and this is the negative of the sum, and 1 is just 1. So we can use Vieta's dE equals c over a, which equals negative 5 over 2. And negative d over e, or negative d minus e, equals negative d plus e, which equals b over a, which equals 3 over 2. So our answer is just negative 5 over 2 plus 3 over 2 plus 1. And this is just 0. Thus, we are done. So this is actually a very clean solution without actually finding the values of d or e. And that's how you should try to solve a polynomial problem sometimes. Because it can get really disgusting if we try to use quadratic formula and plug them into this and then, yeah, so on, blah, blah, blah. Yeah, so basically we would expand this and we realize that d is product and g plus e is this is the most key concept that you would need to know in order to basically solve this problem. All right, our next problem is sum of the reciprocals of the roots of the equation. So we multiply both sides by x, and now we have a quadratic. And this quadratic, so we want to find the roots. Let's call the roots a and b. So we want to find 1 over a plus 1 over b. So if we multiply both sides by ab, this is actually equal to ab, a plus b. Not multiplied by ab. But if we get a common denominator, we get this. We want to find this, and we realize this is the sum of the roots over the product. Thus, we know that the sum of the roots was negative b over a. Negative b over a over c over a, which equals negative b over c. So then if we just put it in here, negative b is negative 1 over 1, which equals negative 1. And that is our answer. So another problem that we solve without actually finding the roots of the problem. Excuse me. So we can generalize this Vieta's formulas to higher degree polynomials. And we need to know what elementary symmetric sums are. So basically you can read this. An elementary symmetric sum is a multiset that's similar to a set but can contain duplicate numbers. And the internal product of the multiset is product with consider a multiset of n numbers and then consider all the multisets containing k of the numbers. The kth elementary symmetric sum is a sum of the multiset of n numbers, or is a symmetric sum of the multiset of n numbers is a sum of all internal products of the multisets with k numbers. So this definition can actually be very complex. So for an easier understanding, we can look at an example. So if n equals 3, then the first elementary symmetric sum would be s of 1. Basically, since we're looking at the first, we would have sets that only contain one element. So it would be just x, y, and z. Now, let's erase all of this. and continue with our second elementary sum. So in this case, we have to choose 2 out of the 3. So it would be xy plus xz plus yz. And our third elementary sum is just all 3 of them, which is just x times y times z. So now that we have a good understanding of elementary symmetric sums, we can dive into generalizing the Vieta's formulas. Now, I'll give you a moment to just read these theorems. So now that you have some time to read it, let's go over it. So if we have n roots, so the polynomial p of x equals a of n x to the power of n plus a of n minus 1 x to the power of n minus 1 and so on, then we can denote the s of k as a kth elementary symmetric sum of the set of n variables. Then s of k equals negative 1 to the power of k of a of n minus k over a of n. So we won't prove this today because for higher degrees it's very batch and complicated, and it remains unimportant for students and for AMC levels. But let's go through a few examples. So let R, S, and T be 3 roots of the equation x 8x cubed plus 1001x plus 2008 equals 0. Find R plus S to the power of 3 plus S plus T to the power of 3 plus T plus R to the power of 3. Oh wow. So basically, R plus S plus T equals 0. Now, how do we know this? All right, so let us copy the formula down. That's the most ugly looking X I've ever seen. I forgot what the thing was. Let's go back. Plus 2008. So basically, we remember that the sum of the roots is negative b over a. However, we realize that there's no x squared term, so this just must equal 0, which is where we get this. Now, we can manipulate this. Since we now know why this is equal 0, then we know that if we subtract t from both sides, we get this, this, this. Like, these are all true. Because we're subtracting t, we're subtracting r, we're subtracting s from both sides. And then we go back. And we realize, like, wow, it's literally what we want to find in here. So we can now see that r plus s minus t, s plus t cubed plus t plus r cubed equals negative t cubed plus negative r cubed plus negative s cubed, which equals negative t cubed plus r cubed plus s cubed. And well, this is much simpler for us to deal with. I can charge my computer. And I was like, all right, I had to charge my computer because it's like losing battery. But hopefully you can see this and this will be much easier. So we can clear our drawings. Now that we've simplified it to negative r cubed now we remember this actually. So we just actually need to find what this is, and then we can find the negative of it. So There's a nice factorizing trick that we like to use that involves r cubed plus s cubed plus t cubed, and that's subtracting 3rt. And then this actually equals r plus s plus t times rs plus rt plus t. I might not like the factorization. I think factorization. Sorry, give me one moment. Oh yeah. Okay, so basically, if we go back on our conics, I was actually doing this incorrectly. We can use a symmetric sum for cubes, and for this, and basically, that's gonna give us, um, it'll be 3s of 3, basically where 3s of 3, s of 3, and we know that s of 3 equals negative 2008 over 50, negative 2008 over 8, which equals negative 251. So then our answer will be negative 750. So P of 3 would equal negative 753. And then since we want negative P of 3, our answer would be 753. All right, now we have a USA MCA a question. So basically, if we have 5 roots, a, b, c, d, e, of the polynomial f of x equals x to the power 4 plus 2x plus 4, then how do we find the value of a squared over, or this expression right here? All right, I'll give you guys some time to think about the problem. Something that I immediately see is that all of these functions, they or the expression that we want to find, it looks very symmetrical. So basically, because it's symmetrical, um, we can manipulate it into a way that we want to. So we know that f of a equals a4 plus 2a plus 4. However, since a is a root, we get this is 0. So if we subtract, we get negative 4 equals a negative 4 plus 2a. And then we can divide by a, and then we get negative 4 over a equals a cubed plus 2. And now this is very similar. We can plug this actually straight into this bottom thing. So then we get a squared over negative 4 over a equals a cubed or negative a cubed over 4. And we can actually do this for every single one because they're just for each variable. So you actually get negative a all over 4. Oh, my bad. Oh, okay. Wait. If you guys didn't see that, let me share that again. Basically, f of a equals a to the 4 plus 2a plus 4. That's because we're plugging it into here. And then since f of a is the root and equals 0, and then we subtract 4, so let's just go here. Negative 4 equals a to the 4th plus 2a, and then we divide by a, so negative 4 over a equals a cubed plus a, or a cubed plus 2. Now basically this is what we want in the bottom here, so we plug it into every single one. Negative 4 over a, negative 4 over b, and then at the end, we're going to be left with negative a cubed plus b cubed, all over 4. Now, this is very important because as we'll be able to see later, um, we will be able to factorize this and actually simplify it. So, so we can look at each of these separately. Negative a cubed, negative 1/4, cubed, and and basically a cubed is negative 4 over a minus 2. This is also because no, this is also because we remember when we had a cubed plus 2 equals negative 4 over a. So a cubed equals negative 4 over a minus 2. And then we can actually do this for each one. So basically, let me clear some drawings. They're all drawings, I guess. So basically, we get that each expression is equal to 1 over a plus 1/2. And therefore, my thing is lagging. Therefore, we get that all of these equals to 2 plus 1 over a, 1 over b plus 1 over c plus 1 over d. Now, we want to find a common denominator. And basically, we realize that if we look at only the ones that are reciprocals, we get that this will be equal to s of 3 over s of 4. Because the bottom will be ABCD, which is symmetrical root of 4. And the top will just be various lists that consist of 3 of these. So it would be s of 3 over s of 4. And basically, if we plug in Vieta's formulas, s of 3 equals negative 1 cubed A1 over A4. So this would equal -2. Then S of 4 would equal -1 to the power 4 over A of 0 over A of 4, which equals 4. So thus our answer would be 2 minus 1/2, and then our answer would be 3 over 2. Basically, this is what we did. A cubed plus 2 equals -4 over A, which is what we want. And then we would manipulate it based on what we need. Now we are dealing with an USAMO problem. So basically, in the polynomial x to the power 4 minus 18x cubed plus kx squared plus 200x minus 1984 equals 0, the product of two of its roots is -32, and we have to find k. So we can use Vietas, which is like symmetric sums again. So remember, this is -b over a. So we want to really utilize this polynomial. So we know all of these. And then basically we want to manipulate this so that we get what we want. So we realize that CD equals 62 because it would be ABCD over AB, which equals -1984 over -32, which equals 62. So then our second condition becomes -32 plus AC plus AD plus BC plus BD plus 62 equals K. And that AC plus AD plus BC plus BD equals K minus 30. So just following along with what I'm doing. Basically, yeah, equals. And we know this because we're given this that to log off to -32. So we get that there's 62, and then basically we can plug that into here. So this becomes 2, and this becomes 2. And then we got these 4 equals K minus 30, because we can these add up to 30, and then we can subtract them from both sides. We have AC plus AD plus BC plus BD equals K minus 30. So let's erase what we don't need. Let's move it up. So this is what we have so far. So now we have something that we have in terms of K minus 30. And then basically we can factor the left-hand side as two polynomials, a plus b times c plus g. So we just need to know what a plus b and c plus g is. And basically we can give them both a variable such that p equals a plus b and q equals c plus d. And substituting our known quantities into the third condition, we know that ab times c plus d plus cd times a times b equals -200. And then we have -200 equals -32 times c plus d plus 62 times a plus b which equals 62p minus 32q. And then our primary condition, a plus b plus c plus d equals 18, gives us that p plus q equals 18, and then p equals 4 and q equals 14. And if we plug them back in, we get k equals 4 times 14 plus 30, which equals 86. So then we have finished. All right, I know that was kind of quick, but now we'll move on to some exercises that I'll give you some time to complete. All right. Hopefully you got some time to work on these exercises. We'll now be moving on to the next section, which is Newton's sums. So Newton's sums is an efficient and clever method to find sum of roots of a polynomial raised to a certain power. So Newton's sums for quadratics. Basically, let R and S be roots of quadratic polynomial. S of k denotes the kth elementary symmetric sum of a set of roots. So P of k equals R of k plus S of k. Then P of k equals P of k minus 1 times S of 1 minus Pk minus 2 of S of 2. For k greater than or equal to 3, P1 equals S1 and P2 equals P1 S1 minus 2 S2. So we have a problem from Brilliant. So we have a polynomial where P of x is x squared minus 2x plus 6 with complex roots a and b. What is the value of a to the power of 10 plus b to the power of 10? This is basically straight up Newton's laws because this is just P of 10. So we know that S of 1 equals 2 and S of 2 equals 6. So using what we know from Newton's laws, we know that P of k equals 2P of k minus 1 minus 6PK minus 2. We know that. And basically, if we continue this all the way to P of 10, and since we know that S of 1 equals 2 and S of 2 equals 6, basically we can apply this recurrence relationship basically until we get P of 10, and we would get our answer of 7552. which is our answer. Now we can generalize. We can check another small case, which is for cubics. Basically, r of k plus s of k plus t of k. Then p of k equals p of k minus 1 times s of 1 minus p k minus 2 s of 2 plus p k minus 3 s of 3. And we can continue this for k greater than 4. And then for k with some smaller values, we can see at the bottom line what we should do. So let's revisit a problem that we covered in the Vieta's formulas. So r plus s plus t equals 0, and r plus s. This is how we solved the way before. So if we think about how we can solve it this time, basically, since we know that we want to find negative r cubed plus s cubed plus t cubed, we can use our Newton's sums for cubics. And basically that would be p of 3 equals p of 2 s of 1 minus p of 1 s of 2 plus 3 s of 3. And we just keep plugging that in, and we would get the same answer of 753. How we would solve that. So we can generalize for all polynomials. So such that x1, x2, x of n be roots of an nth degree polynomial. If s of k denotes the kth elementary symmetric sum, which is to some power, then p of k minus 1 equals p of k minus 2 s of 1. And this is kind of like a recurrence relationship. So we can try some more examples, like let s of k denote the sum of kth powers of roots of polynomial, right here. And we show that s of 0 equals 3, s of 1 equals 5, s of 2 equals 9. Let a, b, c be real numbers such that s of k plus 1 equals a s of k plus b s of k minus 1 plus c s of k minus 2 for k equals 2, 3, 4, etc. So what is the value of a plus b plus c? So that's the question we need to answer. So if we apply Newton's sums, we get s of k plus 1 plus negative 5 of s of k plus 8 of s of k minus 1 plus negative 13 s of k minus 2 equals 0. And thus we have s of k plus 1 equals 5, negative 8, and 13, which are the coefficients we need, and thus our answer is 10. Now we have another example from ALPS. There exists 3 positive integers such that the sum of the integers is 14, sum of squares is 78, and sum of cubes is 476. Some of the reciprocals of these integers can be written as m over n. What is the value of m plus n? So let r s of t be the 3 positive integers. Suppose there are roots of a cubic polynomial, as x cubed plus x squared plus bx plus c. Now, basically, we are given that, like, if r and s t are, then r plus s plus t equals r plus s plus t is 14, r squared plus s squared plus t squared is 78, and r cubed plus s cubed plus t cubed equals 476. So if you apply Newton's sums, we get p of 1 plus a equals 0, p of 2 of a times p of 1 plus 2 of b equals 0. And if we continue this, our cubic polynomial would be x cubed minus 14x squared plus 59x minus 70, which can be factored into x minus 2, x minus 5, and x minus 7. So thus our 3 positive integers would be 2, 5, and 7. Thus our answer is 59 over 70. So the sum of the reciprocals would be 59 over 70, and our answer is 129. Alternatively, you could use guess and check, like 2, 5, and 7 are whole numbers. It wouldn't be that hard. So here are some more exercises for you to work on. Or here are some more exercises for you guys to work on now. All right, due to time, I hopefully you guys can read these to you guys. These slides will posted later for you guys to work on. Basically, we'll move on to graphic transformations. Basically, if p of x has integer coefficients, then a minus b divides p of a minus p of b. So basically, we have vertical stretch and compression here. So for y equals a of f of x, basically where the absolute value of a is greater than 1, then the graph of f of x will be vertically stretched by a factor of a. And if if the absolute value is between 0 and 1, then the graph of f of x will be vertically compressed by a factor of a. Basically, now we're looking at horizontal stretch and compression. So if y equals f of a of x, where a of x is inside parentheses, where absolute value of a is greater than 1, then f of x is compressed horizontally. And if absolute value of a is between 0 and 1, then the graph of f of x is stretched horizontally. To find the coordinates of transform function in this form, you multiply the x coordinates by 1 over a, because basically, since a is inside of parentheses, you would be multiplying by a. So our reflections. So y equals negative f of x, where the negative is out of f of x, is reflection across x-axis because all the y values are being reflected. And then y equals f of negative x, where negative x is inside the parentheses, is when f of x is across the y-axis because all the x values that are being inputted into the function are becoming negative. From horizontal shift, basically y equals f of x plus c will shift f of x left c units. Now this is kind of hard to. So if this is function f of x, then function f of x plus, let's just say 1, is basically just moved over by 1. Now this is because, like, let's just say like f of negative 2 equals 0. In order to plug in negative 2, we need to plug in negative 3 here. So negative 3 would be at 0. So everything is moved over by 1. And vice versa. For vertical shift, basically we would add c to the y value, and vice versa. If we subtract, then it would move down. Now we have example. So this is a transformation that would be enacted on the following equation: f of x equals 4 brackets 6 parentheses x minus 3 to power 4 all minus 7. So basically, this equation is based off the parent function y equals x fourth. So um one thing we can do is we can start at the end or start at the beginning. But if we start at the end, we know that our last since it's minus 7, we know it's going to be transformed, or I guess transform is right, or shifted downwards. We shifted down by 7, which gets rid of this end of 4. And now multiplying by 4, we know that this is a vertical shift. So if we go back, let's say here, remember if a is greater than vertically stretched by a factor of a. So it's going to be vertically vertically stretched by 4. Now we have to deal with this inner layer. Basically, 6 is also vertically stretched by 6. Plus 3, it's shifted to the right by 3. And then we're left with x to the power 4, which is what we had at the beginning. Now we have more exercises. Basically you can find these in the handout later, so I'm just going to skip them for now. We can look at our graphic transformation problems to manipulate roots of a polynomial. So A, B, C are roots of polynomial x cubed minus 21x squared plus 3x plus 2 equals 0. We have to compute a plus 1 times b plus 1 times c plus 1. So let's transform the polynomial into a polynomial where a plus 1, b plus 1, and c plus 1 are the roots. So we can use Vieta's formulas. So basically, we can transform the roots into a polynomial. So that's what. So shifting the polynomial to the right by 1 unit increases our roots by exactly 1, which is exactly what we need. So if we shift every single value by oh yes, I know. Yeah, basically this is the question. X cubed minus 21 x squared plus 3x plus 2 equals 0, and we want to compute this. Basically, this is actually a very nice solution to this. Basically, we shift over by exactly 1, and that basically, or should this way, which the roots will all increase by 1. So now we get x minus 1 cubed minus 21 . All right, basically, I'm not gonna do this. You let x become x minus 1 because we're shifting it over to the right by 1, and basically, we can expand it into a polynomial such that our n value is negative 23, and then since we want to find the product, we find negative, which would be so thus our answer would just be c over a, which is negative 23. So Vieta's formulas trivial solve problem like this. So why do we even use graphic transformation? Well, these transformations are helpful in analytic geometry and calculus and are purely used to human. All right, so our last problem. We need to find a squared plus b squared. We can actually do this with roots like a plus b squared minus 2ab. We can use straight up Vieta's here, which is negative b over a, and 1 squared minus 2. The product is c over a, which is 3, so it'll be 441 minus 6, 435. Thus, we're done. However, we won't be able to transform it with plus or minus square root of x off the bat because it wouldn't be a polynomial anymore. So looking back at this, if we try to become a little bit more creative, we see that if we plug in negative x instead of x, our new polynomial would have roots of negative a and negative b. And if we multiply with the original polynomial, the signs of the roots are canceled and the roots are squared. So if we multiply these two new polynomials together, we get x to the 4th minus 435 x squared plus 9 equals 0. And our desired result is 435. It's basically the sum. Which is basically the sum of the roots, which were a squared and b squared. And we are done. All right, thank you for coming today. That was the end of our the class number 3, and I hope you're
All right, I'm stopping the recording now.